Okay, good morning to everyone. So today we are just going to end this topic, that is the introduction to digital communication. We have only one slide to remain. So already we have discussed regarding the ideal pulses. So these are the ideal pulses where there is no transition time between the change of states. Okay, so when a pulse is change the states from low to high, then it actually changes its states instantly. Okay, so no transition time is actually identified over here. Okay, but practically it is not possible. Practically some time required uh, to change the level from the low to high. Okay, so you see the rise time is defined as the time taken by the pulse to rise from 10% to 90% of the pulse amplitude, and the fall time is defined as the time taken by the pulse to fall from the 90% to 10% of the pulse amplitude. So what it does mean, so if you just see this pulse shape, so it is the practical pulse. Suppose let us assume, the maximum amplitude is V volt. Okay, so maximum amplitude of the pulse is the V volt. Okay, so the time taken by the pulse to rise from 10% of V to 90% of the V means 10% of V to 90% of V means 0.1 V to 0.9 V. The time taken by the pulse to change its amplitude level from 0.1 V to 0.9 V. Okay, so if you just see very carefully, this is your 0.1 V and this is your 0.9 V. So this is the time where you have 0.1 V and this is the time where you have 0.9 V. So this time duration is the rise time T suffix R. Okay, so that is why it is written the rise time is defined as the time taken by the pulse to rise from 10% to 90% of the pulse amplitude. Okay, and the fall time is same. You see, this point is 0.9 V and this point is 0.1 V. So time taken by the pulse to fall down from 0.9 V to 0.1 V. Okay, so this time, so here this is the time instance where the amplitude is 0.9 V and this is the time instant the amplitude is 0.1 V. So this time is the fall time. Okay, so you see there the pulse need a certain finite time to rise from 10% of the maximum amplitude to 90% of its maximum amplitude. The 10% of the amplitude is 0.1 V in this case, and 90% of the maximum amplitude is 0.9 V for this case. Okay, same thing, the pulse takes the time to go down from 0.9 V to 0.1 V. That is the fall time. After that, the pulse width. What is the pulse width? So the pulse width, it also can be defined. You see, the maximum value is V volt. 50% of V, that is actually 0.5 V. And if you see, this point is actually 50% of V. This point is actually 50% of V. Now you have to check the time instance where the 50% of the amplitude appear. So if you check in the rising edge, so this is what? This is the leading edge. And this is what? This is the trailing edge. So first you need to point out the 50% of V on the leading edge as well as on the trailing edge. Just 1 minute. Just give me a time. Just. Okay, so now the time duration between this 50% of the amplitude, the 50% point on the leading edge and trailing edge is actually the pulse width, which is defined by TW. Okay, so if you just see, it is written here, the duration of the pulse is usually identified by the pulse width T suffix W, which is defined as the time between the 50% points on the rising and falling edge. So here we have pointed out the 50% point on both the rising and trailing edge, and the time duration between these 2 points is actually the pulse width TW. Okay. Now, reciprocal of the period is the frequency of the periodic waveform. So we always know, we actually quite familiar with this term. So this is actually your sine signal. So you see, this is one cycle. So it starts from 0, completes the positive half cycle, then completes the negative half cycle. So this is the complete one cycle. The time duration of the cycle is capital T. So this is the fundamental period. After T second, the pulse, the cycle repeats itself. After T second, you see the same cycle you will get. So the fundamental period is capital T, and 1 by capital T is the fundamental frequency. And you know the sine, cosine, square pulse train, rectangular pulse train, all are periodic in nature because it repeats itself after every T second. Okay. Now, what is the duty cycle? Now, duty cycle is also very simple. Duty cycle is actually, okay, suppose so this is the periodic pulse train. This is the one period, capital T, and over this one period, you can observe it is the on state and it is the off state. Why? Because here the voltage level is high and here the voltage level is low. Okay, so the duty cycle will be T on divided by capital T. Okay, this is the duty cycle. So out of the one period, for how much time the pulse is in the on state. That is the duty cycle. That is the ratio T on by T. Okay, the ratio of the time for which the pulse is at the on state divided by the time period. Okay, so this is the duty cycle. Now we are going to discuss about the numbers with different bases. So we know we have the decimal number, which has a base 10, then binary number, then octal number, and then hexadecimal number. So we will discuss about the number system today, complements and all those things. So right now we will discuss about the decimal number. What it is, suppose you have the 7392. This is a decimal number. How could you express it? The process is very simple. The 7 into 10 cube plus 3 into 10 square plus 9 into 10 to the power 1 plus 2 into 10 to the power 0. So in this way you can express it. And the coefficients are this coefficient is A3, this coefficient is A2, this coefficient is A0, and A1, and this coefficient is A0. So these are the coefficients. A3, A2, A1, and A0 are the coefficients. So what you are doing, you are actually multiplying the coefficient with the power of 10. And this suffix is actually defining the position of the coefficient. This is the 0th position, this is the first position, this is the second position, and this is the third position. So A3 will be multiplied by 10 cube because A3 is at the position number 3. Then A square will be multiplied by 10 square, A2 will be multiplied by 10 square, A1 will be multiplied by 10 to the power 1, and A0 will be multiplied by 10 to the power 0. So in this way, you can actually represent a decimal number. And suppose you have this type of number, example, A3, A2, A1, A0, point A minus 1, A minus 2, A minus 3. Base 10 means it is in the decimal number. The base is 10. So how could you so what is happening here? The coefficients have given. So how could you represent this decimal number? It is very simple. So A3 into 10 cube plus A2 into 10 square plus A1 into 10 to the power 1 plus A0 into 10 to the power 0 plus A to the power minus 1, because you see here suffix is minus 1, so power of the 10 will be also minus 1. Then A minus 2 into 10 to the power minus 2 plus A minus 3 into 10 to the power minus 3. So in this way, you can able to get the decimal number, and one decimal point is also involved in this case. Okay. So I can write the decimal number is said to be of base 10 because it uses 10 digits. 10 digits means from 0 to 9. Okay. From 0 to 9, because you see, if you just take this example of 7392, if you observe all the digits are between 0 to 9. Okay. So the decimal number is said to be of base 10 because it uses 10 digits. and coefficients are multiplied by the power of 10. Okay. So first of all, the digits are between 0 to 9 and the coefficients are multiplied by the power of 10. Right. So that is why it is the base 10 system. Decimal is the base 10 system. So if you want to just describe the decimal number, it will be something like this: 7392 base 10. So this is a decimal number. Okay. Now the binary number. It is what? It is the base 2 system. Because in case of binary, the digits between, or sorry, not between, the digits are only 0 and 1. Two distinct values. Which are 0 and 1. Okay, and also in this case, the coefficients will be multiplied by the power of 2. Okay, so coefficient will be multiplied by the power of 2. Suppose, for example, 11010.11 base 2. Now, how to convert it a decimal number, base 10 number? You are changing your base from 2 to 10. So how could you do that? You see, this is the 0th position, so the coefficient is A0. This is the first position, the coefficient is A1. This is the second position, the coefficient is A2. This is the third position, the coefficient is A3. And this is the fourth position, the coefficient is A4. And here is the point involved. Then towards the right hand side, this is A minus 1 and this is A minus 2. So how to do that? Now A4, this is the coefficient. This will be multiplied by power of 2. So 2, what will be the power?
4.
Plus A3 into 2 cube plus A2 into 2 to the power 1 plus A1 into, 2 square, A1 into 2 to the power 1 plus A0 into 2 to the power 0 plus A minus 1 into 2 to the power minus 1 plus A minus 2 into 2 to the power minus 2. And now you see what are the values of A4. Okay, the A4 is equal to 1, A3 is equal to 1, A2 is equal to 0, A1 is equal to 1, A0 is equal to 0, A minus 1 is equal to 1, A minus 2 is equal to 1. So what will be the equation then? 1 into 2 to the power 4 plus 1 into 2 cube plus 0 into 2 square plus 1 into 2 to the power 1 plus 0 into 2 to the power 0 plus 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2. So you will have 16 plus 8. For this you will get 0 plus 2. For this you will get 0 plus. This is what? Half. And this is what? 1 by 4th. So you have 26 plus, for half you have 0.5, for 1 by 4 you have 0.25. So it is 26.75 base 10. Okay. So this is the way you can convert a binary number to the decimal. Okay. So in general, the base R system. Base R can be anything. Octal, okay, for binary R is equal to 2. For decimal, R is equal to 10. For octal, R is equal to 8. For hexadecimal, R is equal to 16. So when you will represent a hexadecimal number, the base will be 16. When you will represent the octal number, the base will be 8. Okay. So generally in the base R system, any number can be represented in base R system a number can be represented as follows, that is an into r to the power n. An means coefficient, right? And an will be multiplied by the power of r, because it is a base R system. I am writing the generalized equation, plus a n minus 1 into r to the power n minus 1 plus a n minus 2 r to the power n minus 2 plus dot 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 plus a1 r to the power n plus a0 r to the power 0 plus a minus 1 r to the power minus 1 plus a minus 2 r to the power minus 2 plus dot 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 plus a minus m r to the power minus. So this is the general expression, where this an minus 1, an minus 2, a minus m, those are the coefficients. Okay. So right now, if you suppose, for example, if you have 4021.2 base 5, so how could you convert it to the decimal? You see, this is A4, this is A3, this is A2, this is A1, and this is A minus 1. So how to do that? 4 into 5 to the power 4 plus 0 into 5 cube plus 2 into 5 square plus 1 into 5 to the power, sorry, I am sorry. This is A0, this is A1, this is A2, this is A3. So 4 into 5 cube plus 0 into 5 square plus 2 into 5 to the power 1 plus 1 into 5 to the power 0 plus 2 into 5 to the power minus 1. So this is 125. 125 into 4 means 600. Plus this will be 0. Then you have 10 plus you have 1 plus you have 2 by 5. So it is 611 and 2 by 5 means I think 4.4. Okay. Oh, I think it is 500, right? 125 into 4. Yeah. 500. Sorry. This is 500. So this is.
Sir, could you please move to the previous slide once?
Yeah.
Yes, sir. Done. Thank you, sir.
Okay. So this is the, sorry, it is not base 5, it is base 10. Okay, this is the base 10 system. Right. So here you see, here you are going to convert a base R system to base 10 system. So how could you do that? You have to multiply the coefficients with the power of 5. Then you will get the decimal number, right? Now hexadecimal. Now in the hexadecimal, the base is R is equal to 6. Sorry, 16. So the numbers will be 0 to 15. In the hexadecimal system, we have the numbers from 0 to 15. Means like the decimal system, we had 9 digits. Sorry, we have the digits from 0 to 9. Okay. In the decimal system, what we had? In the decimal system, we had digits from 0 to 9. For binary system, we have digits 0 and 1. And now for the hexadecimal, we have the number from 0 to 50. Now the very interesting thing is that from 0 to 9, we borrow from decimal system. And also 0 to 9 are the digits. But when you are going for 10, 11, 12, 13, 10, 11, 12, 13, 14, and 15, these are numbers. Because these numbers actually contains the digits. Okay, so in the hexadecimal system, we have the numbers from 0 to 15, and out of these 16 numbers, 0 to 9 will be borrowed from decimal system, and the rest of the numbers, that is 10, 11, 12, 13, 14, 15, that will be represented by the letters. So we have 10, 11, 12, 13, 14, 15. So these numbers will be represented by the letters, and the letters will be A, B, C, D, E, and F. And 0 to 9 comes from the decimal system. And 10, 11, 12, 13, 14, 15, these will be represented by these letters. Right? So, suppose you have B, 6, 5, F, base 16. So, you convert it to the decimal number. How could you do that? So, you have what? You have A3 is equal to B, A2 is equal to 6, A1 is equal to 5, and A0 is equal to F. So you have to multiply the coefficient with the power of 16. After that, you will get the decimal number. So A3 means B, and B means 11. So 11 into 16 to the power 3. You have to understood that 10, 11, 12, 13, 14, 15 represented by the letters. So it is the way of representation. But when you will try to convert the hexadecimal number into the decimal, and here you see, you have to, this is actually what? This is equivalent to B, which is at the position 3, and it is multiplied by the power of 16, where the power of 16 is 3. Because if you observe this coefficient, at the suffix 3 is there. So that is why B will be multiplied by power of 3. But when you are doing the calculation, you have to take the exact value of B, and which is 11. So that is why I have written 11 into 16 cube. Okay, so if you do in this way, so 11 into 16 cube plus 6 into 16 square plus 5 into 16 to the power 1 plus F. Now what is F? F means 15. So 15 into 16 to the power 0. So if you do this calculation, you will have 46687 base 10. Okay. Now we will go for binary addition, subtraction, and multiplication. How could I do that? Okay, so example of the addition. Right. So you have 1 0 1 1 0 1, and then you have 1 0 0 1 1 1. So the first one is the augend, and the second one is the addend. Now you will do the addition. So when you will add this 2 1, the sum will be 0 and you will have carry, and that carry will be added to the next higher position. Then you again you have 1 and 1, so this sum will be 0. Then again you have a carry, so you have 3 ones right now. So you have, when you will add this 3 1, what will happen? 1 1 0, the sum will be 0, and then 0 will be added with 1. Again you have 1, and again you have 1 carry, which will be added to the next higher position. You have 1 1, so you will have 0, and then again you have a carry, which is 1 over here. Then again you have 1 1, so you have 0 and 1 carry. So this is the sum, binary addition. Okay, now we will talk about the subtraction. So we have 2 digits, binary number 1 0 1 1 0 1, then 1 0 0 1 1 1. So this is minuend, and this is subtract. So right now we will do the subtraction. So 1 will be subtracted from 1, so you will get 0. Now in the next position, 1 will be subtracted from 0. So what you will do, in the decimal system, what we are doing, the decimal system, if you just observe, suppose we have 10 and then we have 8. How could I do that? We borrow, actually, actually 10 from the next higher position, I think. Right, this will be 10, na? So you have 2 and then you do the -1, that is why 0 2. In this way we have done the subtraction. Same thing we will do over here, because it is the base 2 system. So I think I will borrow 2, so it will be 1, and again I have to subtract -1. So 1 minus 1 0, and then again you have 0 minus 1. So the result will be 1, and then again you have -1. So you have 0, and then 0, then 0. Okay. So in this way you will do the subtraction, right? Now the second
Please once more explain subtraction.
Huh?
Please once more explain subtraction.
Subtraction is what? When you have 0 and then you have 1. You are subtracting 1 from 0. So your minuend is high. Okay, M is greater than S, right? For this case, you are subtracting 1 from 0. So in the decimal system, what you have done, when you are subtracting, suppose 15 minus 7, what you have done? Here you see, if you concentrate on this part, the 5 is less than 7. So actually you are subtracting one quantity which is greater than 5. So what you have done, I think you have add 10 over here. So you have 8, and again you minus to the -1. So you have 0. Why we are adding 10? Because it is a decimal system and the base is 10. But here it is the binary system, so the base is 2. So what I will do, I will borrow from the next higher position. So it will be 1, and I have to subtract 1 from the next higher position. Okay. So that is why I have doing that the thing I am doing here. Here you see I am subtracting 1 from 0. So that is why +2. So 2 minus 1 is 1. And due to this borrowing, I have to subtract 1 from the next higher position. And you see, you have right now 3 1 to subtract. So you subtract this to 1, you will get 0. And again, you have another 1. So actually, you are again subtracting 1 from 0. So that is why the result is 1. And again, here is a -1 because you have to borrow 2 from the next higher position. And then again, you have to subtract -1 from the higher position. So that is why 1 minus 1 is 0. And then again, you have 0 minus 0, 0, 1 minus 0 is 0. Okay.
Yes, sir.
Now the multiplication. Very simple. It is the multiplicand. Okay, 1, 0, 1, 1. And then you have 1, 0, 1. So this is multiplicand and this is multiplier. And just do the multiplication, the same rule. 1, then 0, 1, then 0, 0, 0, 0, then 1, 1, 0. Then you add 1, 1, 1, here is 0, 1. Okay? Now, another example, 1010.011 base 2 system, you have to convert it to the decimal number. And again, another thing is that you have 630.4 base 8 octal system. You have to convert it to the decimal number. Another example. So you know it is very simple to do. What is the methodology? You have 1 into 2 cube because it is the third position plus 0 into 2 square plus 1 into 2 to the power 1 plus 0 into 2 to the power 0 plus 0 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 plus 1 into 2 to the power minus 3. So you have 8 plus 2 plus this will be 0, this will be 0, this will be also 0. Then you have 1 by 4 plus 1 by 8. So you have 10 plus, it should be 3 by 8. So how much it is? 3 by 8. This is actually 10 plus 0.375. So 10.375 is simple. Next, octal system. You have to add, multiply the coefficients with the power of 8 and then you have to add. So 6 into 8 square because it is 0, 1 and 2 plus 3 into 8 to the power 1 plus 0 into 8 to the power 0 plus this is a minus 1, so 4 into 8 to the power minus 1. So this is how much? This is 64 into 6. This is 384 plus 24 plus this is half, minus 0.5. So you have 804.5. This is the base 10. Okay. Now another example. 41. This is the decimal system. Then you have to convert it to the base 2 system. When decimal to binary. Now in this case, you have to do the division. Okay, by 2. Here, what you have done? You had multiplied the coefficient with the power of 2, and in the second case, you had multiplied the coefficient with the power of 8 to obtain the decimal numbers. Now you have to go in the reverse direction. You have to come from decimal to binary. So in that case, you have to do the division, but with the base of this 2, because you are going to the binary system. So you have to divide this 41 by the base of the binary system. So 41 divided by 2, that is 20. Then 2, just sorry, this is 1 actually. This is 2, 0. This is 2, 0. This is 2, 1. This is 2, 1, 0. And you have to go in this way from this point, from down to up. So you have 1, 0, 1, 0, 0, 1. This is the binary system. You can obtain from the division of the 41 by 2. Okay. Now another example. This is the decimal number 153 base 10. You have to convert it to the octal. How to do that? Same thing. You have to divide this 153 by 8 because you are going from decimal to octal. So 153 divided by 8, you have 19. The remainder is 1. Then remainder is 3. Okay, then you cannot divide it. So you have to go in this way from downward to upward. So your octal number is 231 base 8. Right? Now, we will take some other examples. Now the example is a little bit different. 0.6875 base 10 to the decimal. How to convert it? Now here the situation is totally different. The situation is different means here you cannot do the division. What you have to do, the procedure is something like this, 0.6875, then this quantity will be multiplied by 2. Then you will have one integer part and you will have a fraction part. Okay. So you have to continue this process until or unless the fraction part will be 0 or until or unless you can achieve the better accuracy. So here you will not do the division. Here you will go for the multiplication, multiply by base 2. So if you do this multiplication, you have integer 1 and then fraction 0.375. Means the total number is actually 1.375. So I am dividing it into the two parts. One is the integer, which is the 1, and another the fraction part is 0.375. Right now, again, I will take this fraction in the next level, 0.375, and then again multiplied with 2. And if you do that, I think you have 0.75. So the integer is 0 and the fraction is 0.75. Now again I will take this fraction 0.75 and I will multiply by 2 and I will have 1.5. So integer is 1 and the fraction is 0.5. Again I will take this fraction 0.5 and again I will multiply it by 2. Then it will be what? 1, only one integer 1 plus 0. Now you see here your fraction part is 0. So you can stop the process. Okay, and here this will be your, now you have to take only the integers because you see it is in the binary form 1011. I will not take this fraction part. If you observe the integers, it is in the binary form. It is a minus 1, a minus 2, a minus 3, a minus 4. In this way, these are the coefficients. So the binary number is nothing but 0.1011 base 2. Okay. So this is the binary number.
So I didn't get this last one. Could you please explain it?
Which one?
This very question on the page right now.
Okay. So means total new mathematics, right?
Yes, sir. Like what we did for the decimal system, that I didn't get.
Okay. So when right now it is what? It is the fraction, okay, in the decimal, you have to convert it to the binary. In the last cases, what you are doing, you have a integer 41 base 10, you have converted it to the binary. So what you have done, you have divided the 41 by this base 2, and you will check the remainder. When you divide the 41 by 2, the remainder is 1. When you divide the 20 by 2, the remainder is 0, and so on. And you are taking the remainder part from and you are actually moving from down to up. Okay, so
Yes,
this is
sir.
the case for an integer. When it is in the decimal number system and you convert it to the binary, then you will do the division only. But here you see the problem is a little bit different. Here you can observe it is the fraction only, and it is in the decimal, and you have to convert it to the binary system. Now, instead of doing the division, I will do the multiplication, and the multiplication I will do with this base 2, because I am converting this decimal number into the binary, and in the binary system the base is 2. In the previous case, I have divided the decimal number, that was integer actually 41, by 2, but here the fraction is given to us in the decimal number system, and I want to convert it to the binary number system. So I will multiply. Now the process is little bit different. Instead of doing the division, I will go for the multiplication, and this fraction will be multiplied by base 2. And now you see the first multiplication. If you do this multiplication, the answer is actually 1.375. Now this answer is divided into the two parts. First one is the integer. In the 1.375, the integer part is 1 and the fraction part is 0.375. That I have divided in the right hand side. Now, what is the procedure? Means until when you will continue this process. Okay, unless the fraction part will be 0, or you will achieve the sufficient accuracy. Okay, so you see, when you have done the first multiplication, the fraction part is 0.375. Then again you will take this fraction part, and that is why this fraction part is written over here, and you are multiplying by 2 again. And you just check the fraction part is 0 or not. And you see the fraction part is also present, 0.75. Then again you will take this 0.75. Here you have written 0.75, and we are multiplying this by 2, and we have a value 1.5, and 1.5 is divided into the two part. The integer is 1 and the fraction is 0.5. You see the fraction is not again 0. I will take this fraction, and I have written the fraction over here and multiplied it by 2, and this result is nothing but 1. So 1 means only integer part present and fraction part vanish. So right now it is the time to stop. We have achieved the sufficient accuracy, and what values we will observe? We will try to take these integer values, whatever I am getting from the multiplication process. So now the first value will be at the -1 position, the second value will be at the -2 position, the third will be at the -3 position, and the fourth will be at the -4 position. So a -1, a -2, a -3, a -4. These are the coefficients. So finally you can write 0.1011 base 2.
Yes, sir. Understood.
Okay.
Yes, sir.
Now the another example. Suppose you have 0.513 base 10 and you want to convert it to the octal system. Now you have fraction, then again you want to convert it to the octal system. The process is same here. You have to do the multiplication, but instead of multiplying by 2, you have to multiply by 8, because you are going to the octal system. So here you have 0.513 multiplied by 8. You have the integer plus fraction. So that will be, I think, 4.104. 4.104. So 4 is integer and 0.104 is fraction. The fraction part is not 0. So you will take this fraction part again, 0.104, and again multiplied by 8. So it is how much? It is, I think, 0.832, right? So integer part is 0. The fraction is 0.832. Fraction is not 0. Again, you will take this 0.832 into 8. And it is give you 6.656. So integer is 6 and the fraction is 0.656. You see the fraction is not 0. So again you take this one, 0.656 into 8, and you will get 5.248. 5 plus 0.248. And again take this 0.248 into 8, then you have 1.984, 1 plus 0.984. Then you see, you can see there the fraction is not 0. Again you take 0.984 into 8 and you have 7.872. So 7 plus 0.872 and so on. And you see there is no possibility of having the zero fraction. Means there is no possibility. Right now I am observing that your fraction part becomes 0. So in this case, in the last case, it was very easier for us that fraction part becomes 0 and we can stop this process. But in this case, the fraction part is not becoming 0. So now you have to stop your procedure, because we think we have already actually achieved the sufficient accuracy. Because if you just check, after the decimal point, 0 point, we are further going for a minus 1, a minus 2, a minus 3, a minus 4, a minus 5, a minus 6. So after decimal, we are going for 6 points. Okay, you can further continue this process for another 2 or 3 steps, but I don't think so. If you do another 3 or 4 steps, your fraction will become 0. So when you will do this calculation, you can automatically understand your fraction will become 0 or not. If it will become 0, then it will be easier for you to stop the process. But if it will not becoming 0, then you can do this process for 6 or 7 places after the decimal point. So here we have done this process after 6 decimal points, maybe 6 decimal or octal points right now. Okay, so right now it will be 406,517 base 8. I will take this only integers. Okay, so this is the another example, right? Now octal and hexadecimal. Okay, so octal means what? 2 cube. Hexadecimal means what? 2 to the power 4. Okay, so suppose you have a number 10, 110, 001, 101, 011, point 111, 100, 000, 110, base 2. Now you have to convert it into the octal number. How could you do that? Okay. How could you do that? In case of binary decimal, it was easy. What you have done, you have multiplied the coefficient with the power of 2, but here you are going from binary to octal. So how could you do that? Already I am telling you the octal means 2 cube. So what I will do you have any clue how to do that? I will start from this point and I will go to the left hand side, and from this point I will go to the right hand side, and I will make a group of 3 binary bits. 3 binary bits. 3 binary bits. 3 binary bits. Because octal means what? Octal means 000 001 till 111. So that is why I am making the group of 3. And in this case, I am going to the right hand side, and again I am making the group of 3. And what is 011? 3, 1015, 0011, 1106, and this is 2. And here it is 7, then 4, then 0, then 6. So octal means, what is the octal number then? 261, 261, 53.7460. That's it. Simple. You have to make the group of 3 because the power of octal means 2 cube, and also the number range the value in the range of 0 to 7, from 000 to 111. So each number containing the 3 binary bits. That is why I am making the group of 3 bits. Just give me one moment. Just I will tell you the hexadecimal. So just the same example. So in case of hexadecimal, this is base 2, and you have to convert it to the hexadecimal number. So the process is very simple. Now in this case, you have to make a group of 4, because hexadecimal means it is the power of 2. And here the numbers, and in the hexadecimal case, it is starting from 0000, 0001, then 1111. So you have to make a group of 4. So from this point, you will go to the left hand side, and here you are making the group of 4. So 00 you can put over here, group of 4, and you have to go to the right hand side, and again you will make the group of 4. So 1011, it means 11, and 11 should be represented by B. 0110 means it is 6. 1100 means 12, so it will be represented by C, and this is 2. This is 1111 means 15, it will be represented by F, and again 0010 means it is 2. So finally you have 2C6B point F2 base 60. Okay, so this is the hexadecimal. So I'll stop here. Send me the attendance. So I'll continue this number system in the next class. I will discuss about the 1's complement, 2's complement, 9's complement, 10's complement, and how to do the subtraction with the complements.